In this module we are going to talk about curves that are defined in polar coordinates, and so of course the first thing we need to do is take a look at what it means to use polar coordinates. So a system of coordinates in the plane, and for now we're going to focus on the plane, is a way to give coordinates to each point in the plane, and we do that by giving an ordered pair of coordinates. And what you're used to is a Cartesian system of coordinates where the two coordinates represent the projections on two axes. With polar coordinates to represent a point in the plane, we're going to represent it with respect to a system that is given by fixing one point in the plane that we're going to call the pole, and we're going to draw one half ray with one end at the pole that is called the polar axis, and to locate the blue point we're going to locate it with respect to this system. On the polar axis we also have a unit of length, and we're going to draw the half ray joining the pole with a point, and on this half ray use the unit of length we have to look at the distance between the blue point and the pole. Let's call that r. And then we're going to look at the angle between these two half rays, between the polar axis and the half ray joining the pole and the point you want to locate. Let's call that theta. So theta here is the angle between the polar axis and the half ray joining the pole and the point. And the pair r theta, where r is the distance to the pole and theta the angle between the polar axis and this half ray, are the polar coordinates of this blue point in the plane that we wanted to locate. Now the first observation that you may have is what does that mean, the angle between the polar axis and the half ray joining the pole and the point, if we're looking at the pole itself? Clearly we need to set a convention for the coordinates of the pole, and if r is 0, we're going to use a convention that we can use any angle for theta, and we still have a pair of polar coordinates for the pole. So that means that we may have more than one pair of coordinates representing the same point. Now in the geometric interpretation I just gave, I assume that r is the distance from the point to the pole and therefore is non-negative. However, we will see that we can also take negative values for r. But before we even get to that, you can see that the fact that we don't have a unique set of polar coordinates also comes from the fact that we can use various measures of the same angle. For instance, we can add an arbitrary number of turns and we end up with another set of polar coordinates. So for instance, if I fix a positive r theta and r 2 pi plus theta represent the same point in the plane in polar coordinates. And similarly, I could decide to rotate in the opposite direction, and again I would get another polar representation for the same point. So for instance, r theta minus 2 pi is another set of polar coordinates for the same point that has polar coordinates r theta. Additionally, as I mentioned before, we could consider the case where we allow r to be negative with the following convention, that if I point in the direction theta, so in a half ray that fixes the direction, and I take a negative r, then I'm moving negatively on that direction, just like on the real line you have a positive direction, or you can represent negative 2 by moving 2 units of length to the left of the origin instead of to the right of the origin. So we could do the same thing and say, well, if I have negative r, for instance, I move by the distance r, but in the opposite direction, and I obtain a point of polar coordinates negative r theta. So that means that I could take the polar coordinates negative r theta, or theta plus pi coupled with the distance, the positive distance r. Right? So if I point in the direction theta plus pi, then I go positively a distance of r. Or I could point in the distance theta and go negatively a distance of r. And I would end up at the same point. So there are many pairs of polar coordinates for each point of the plane. Now we could force unique representation for points that are not the pole. Right? We've seen that at the pole we can take any angle by restricting yourself to a non-negative value of r and the angle theta between 0 and 2 pi, excluding 2 pi to avoid to repeat the same direction twice. But in general, unless we specify these conditions, we're not going to do that, to take these restrictions, and therefore we're going to allow for multiple polar representations of the same point. So as an exercise to see how this system of coordinates work, we're going to plot the points of polar coordinates 1 pi over 2, negative 2 pi over 4, and 3, 2. So we start with our polar system, which consists of one specified point, the pole, a polar axis that has the pole as one of the ends, and a unit of length on this polar axis. So to represent this point of polar coordinates 1 pi over 2, 1 corresponds to the distance to the pole, and pi over 2 the angle between the polar axis and the half ray joining the pole and the point. So first we need to look at the angle pi over 2. We are pointing in the direction that makes an angle pi over 2 with the polar axis. In other words, we are pointing in this direction. And now we go at a distance 1 from the pole along this direction. So we end up at this point. So this is what you would do to draw these points, to plot them. Moving to the second example, where r is negative 2 and theta is pi over 4. Again, we're going to start with the direction. We point in the direction that makes an angle pi over 4 with our polar axis. And then we go a distance negative 2. That means that we're going to not go in the direction indicating by the arrow on the blue line, but in the opposite direction by 2 units. So there is 1 unit in the opposite direction, 2 units in the opposite direction, and this is our point of polar coordinates negative 2 pi over 4. Then we have a point of polar coordinates 3, 2. The second coordinate corresponds to the angle measured in radian. So this is really 2 radian, which in degrees would be 360 degrees divided by pi, because 1 radian, well, because 2 pi radian is 360, and therefore 2 radian is approximately 115 degrees, which would look like that. So that fixes the direction, and now we go 3 units of length along this direction, 1, 2, 3, here is our point. Now, very often, we're going to use simultaneously Cartesian coordinates and polar coordinates. When this is the case, as a general convention, we assume that we use a specific polar system compatible with the Cartesian coordinates. Specifically, here I have Cartesian coordinates in the plane, here I have polar coordinates in the plane, and what we're going to do is that as a convention, the pole is at the origin of our system of Cartesian coordinates, and the polar axis coincides with the positive x-axis. So we end up in this situation. And now you see that the same point is represented by the polar coordinates r theta and by the Cartesian coordinates x, y. And we can go from one to the other easily, because here we have a right triangle in which x is r times cosine theta and y is r times sine theta, because in that right triangle, r is the length of the hypotenuse, x is the adjacent side for theta and y the opposite side. And similarly, you see that using the Pythagorean theorem in that triangle, we see that r squared is the sum of x squared and y squared, and that the tangent of the angle theta is y over x. So these formulas will give us a way to go from one system of coordinate to the other. So to apply this, let's try to find the Cartesian coordinates of points that are given by polar coordinates. So if I have polar coordinates 2 root 2, 3 pi over 4, what are the Cartesian coordinates? Well, we can use the first set of formulas. X is r cosine theta, y is r sine theta. So let's start with this point. If x is r cosine theta and I plug in r equal 2 root 2 and cosine is 3 pi over 4, well, you might think, are these formulas that I have written, are they still going to work if we don't have an acute angle, like here, because the argument we used was in a triangle. In the second example, we have a negative r, so again, you might be skeptical that the argument we gave before still works, but we're going to see that everything checks out. So in this case, I plug things in even though I have an angle that is not acute, and I get 2 root 2 multiplied by cosine of 3 pi over 4. But cosine of 3 pi over 4 is negative root 2 over 2, and when I multiply things through, I get negative root 2 squared, in other words, negative 2. And for y, I take r is 2 root 2, sine of 3 pi over 4 is this time root 2 over 2, and I multiply things through, I get 2. Does that correspond to the geometric situation? Well, if you take an angle of 3 pi over 4 and you move 2 root 2 along that direction, you see that you get this blue point, which has indeed a negative x coordinate and a positive y coordinate, corresponding indeed to the Cartesian coordinates negative 2, 2. What about if r is negative? Do we have a problem with our formulas in that case? So if I try to just plug things in, I plug r equal negative 1 and theta equal pi over 3, I get negative 1/2 for x, and if I do the same thing for y, I plug r is negative 1, theta is pi over 3, I get negative sine of pi over 3, that's negative root 3 over 2. Does that check out with the geometric situation? If we point in the direction pi over 3 and move negative 1, we end up with this blue point that indeed has a negative x value and negative y value. And this indeed corresponds to the Cartesian coordinates negative 1/2, negative root 3 over 2. So no problem if r is negative, no problem if we have an angle that is not between 0 and pi over 2.